What if I told you there's a cheat sheet for everything you can see, touch, and breathe? A kind of master key that unlocks the secrets of matter itself. Sounds a little like science fiction, doesn't it?
Well, guess what? It's real. This right here is the modern periodic table. And it is, without a doubt, the most powerful cheat sheet in all of science. In the next few minutes, we're going to learn how to read it, not like some dusty old chart, but like a treasure map to the elements. So let's get started with the first big secret. How in the world is this thing organized?
I mean, think about it. How would you even start to organize everything in the known universe? For a long time, scientists were kind of stumped. They tried arranging elements by their mass, but things just didn't quite line up. The real breakthrough, well, it all came down to one single, beautiful number.
It all kicked off with Ernest Rutherford, who discovered the proton. And building on that, Henry Moseley had this huge aha moment. He realized that an element's true identity isn't its weight, but its atomic number. That one insight completely changed the game, fixing all the old mistakes and giving us the elegant table we use today.
Okay, so what is this magic number? It's actually incredibly simple. It's just the number of protons inside an atom's nucleus. That's it. Hydrogen has 1 proton, so its atomic number is 1. Helium has 2. Its atomic number is 2. This number is like a fingerprint. It's what makes an element, well, that specific element.
And with that key in hand, the main rule of the table becomes almost laughably easy. We just line up the elements in order of their atomic number, one after the other. It's this perfect logical progression, from 1 all the way up to 118.
All right, so we've got the basic organizing principle down. Now, let's actually learn the language of this map, because the position of every single element on this grid tells a remarkable story about its inner structure and even its personality.
First up, let's look at the horizontal rows. You see there are 7 of them, and they're called periods. Think of it like reading a sentence. You go from left to right, and when you hit the end, you drop down to the next line and start a new period. Simple enough, right? But what does that new line actually represent? And here is the secret. The period number is a direct clue about an atom's structure. If an element is in period 3, for instance, its atoms have 3 energy levels, or shells for their electrons. Period 4, you got it, 4 energy levels. It's literally that straightforward. Now let's switch to the vertical columns. These are called groups, and there are 18 of them. You want to think of elements in the same group as being like a family. They tend to look and act alike, and there's a very specific reason for that. The secret, once again, is in their electrons, specifically the ones in their outermost energy level. We call those valence electrons. Every single element in the same group has the exact same number of these valence electrons, and they're the ones that do all the interesting work in chemical reactions. And that is the key. Those outer electrons dictate absolutely everything about how an element behaves chemically. They decide who it bonds with and how it reacts. This is why all the elements in a single column share a chemical personality. It's a family trait written right into their atomic code. So, now that we understand periods and groups, we can zoom out a bit and start exploring the table's major neighborhoods. These are big blocks of elements that have shared characteristics, kind of like the famous families of the periodic table. Broadly speaking, the table is divided into 4 main neighborhoods, or blocks. Over on the left, you've got the super reactive metals of the S block. On the right, you have the really diverse P block. Right in the middle are the classic transition metals of the D block. And those 2 rows floating at the bottom, that's the F block. Each neighborhood has its own distinct vibe. Let's see how this plays out. Take the alkali metals in group 1. They're in the S block, they have just 1 valence electron, and they are extremely reactive metals. Now jump way over to the P block and look at the halogens in group 17. They have 7 valence electrons and are also very reactive, but they're nonmetals. And then on the far right, you've got the noble gases, with a full outer shell of 8 electrons, which makes them stable and totally unreactive or inert. Okay, so we can read the table, we can identify the families, but the true genius of the periodic table isn't just about how it organizes what we already know. It's about how it lets us predict what we don't know. It's an incredible predictive tool. You can even work backwards. If you know how an atom's electrons are arranged in their shells, you can find its exact address on the table. The total number of shells, that tells you the period, or its row. And the number of electrons in that outermost shell gives you its group, or its column.
But knowing an element's address isn't just about finding its little box on the map. Its location tells you what kind of properties to expect. It lets you predict how it's going to behave before you even step into a lab. Take chemical activity, for example. You know how eager an element is to react. This follows really clear, predictable trends. For the alkali metals over on the left, notice how that chemical activity increases as you move down the column. But for the halogens on the right, the exact opposite is true.
Let's just make that crystal clear. For the metals on the left side, chemical activity generally goes up as you move down a group. For the nonmetals on the right side, that trend is reversed. Activity goes down as you move down the group. The table doesn't just list elements, it's revealing the rules they all live by.
And these trends let us pick out the champions of reactivity. Following the rule, cesium, way down there in the alkali metals group, is the most active metal of them all. And fluorine, sitting right at the top of the halogens, is the most active nonmetal. The table predicted it all along.
You know, the periodic table is so much more than just a scientific icon. It's a story of discovery, it's a map of matter, and it's a predictive engine that has guided chemists for over a century. It's the perfect summary of what we know about the elements, which leaves us with one final, pretty fascinating question. What will it help us discover next?